Welcome back to our series on probability theory. I'm Mark Ledbetter, and this is lecture video 28, Supplemental. So we are going to talk about the continuous uniform distribution in a little more detail. Last time we talked about the CDF and PDFs of continuous distributions. We gave the example of the uniform distribution as far as the CDF and PDF. We did talk in general about the expected value, the variance, and the MGF. Now we're going to apply it to the uniform distribution. So the uniform distribution is one of the few distributions that has the same name in the discrete and continuous forms or versions, if you will. So as we talked about last time, we have the CDF and the PDF of the uniform distribution. As far as notation, it's important to note that this is how we note it. And you'll notice that these are open intervals, not closed intervals, for the reason mentioned last time, and that is that the derivative of this does not exist at x equals a or x equals b. Okay, so these are good forms to have on your formula sheet. Now let's look at the MGF. So the moment generating function m of t is e, the expected value of e to the tx. So we substitute in e to the tx, and then we substitute in for f of x and dx. So this f of x is a constant because it's uniform, it has a uniform height or a constant height. We can pull that out of the integral and using the property of integrals, and then we're left with e to the tx dx. So if you need to use substitution here, you can for this. You can set this equal to u, and then du is equal to t dx. You can solve for dx, 1 over t, so 1 over t du. And so you would substitute in 1 over t du, e to the u. Take the integral of that, that's e to the u, and of course you still have your 1 over t. And so we end up with substituting back for x and for u with tx. We end up with the 1 over t here, e to the tx, and of course the constant we had to begin with. And then we take from limits x equals a to x equals b, and we end up with this expression, which is true when t is not equal to 0. If t is equal to 0, then we can come back to here and look and substitute in 0 before we integrate or do anything. And so what happens is we end up with the expected value of e raised to the 0, which is e of the 1, expected value of 1. The expected value of any constant is itself, which is 1. Okay. But when we take the derivative of this MGF, we end up with t in the denominator and t squared in the denominator, so we really can't set this derivative, we can't evaluate it at t equals 0. So this does not exist. So we can't use the moment generating function to find our moments. So we're going to have to do this using the expectation, the definition of expectation. So mu is ex, and that is the integral of x, f of x dx. Again, we can pull our constant out to the front. We integrate this, we get 1 over b minus a, 1/2 x squared, and then we evaluate that from b minus a, or that we take the expression, substitute in b, subtract when we have a, and we end up with this expression here. We factor the top. So again, in calculus, we stress factor, factor, factor. Don't combine, but factor. Don't expand, but factor. But in this case, we're factoring, and then we see that we can cancel out these, and we end up with this expression for the mean. So please put that on your formula sheet. It's nice and handy to have. And if you think about it, it's very logical. It's the midpoint of a rectangle is halfway between the length of that side. Okay, so ex squared, again, we take the integral and we end up with a little more complicated expression here. And remember that we have to take ex squared minus ex quantity squared to get the variance. So here is EX quantity squared, we find the common denominator, and when we do this and simplify, we end up with a perfect square, and so this is our expression for the variance. So please take some time to work through the algebra, the integrals in the algebra, make sure you understand it. Okay. So the continuous uniform distribution, the basic one, U01, this is very important uniform distribution. You can simulate this using what we call a pseudo-random number generator. Usually we don't say the word pseudo, but all random number generators are pseudo because the programs that produce these so-called random numbers have what we call a seed number or starting number. And so if you know that, then you can get all of the subsequent numbers that are generated using some, they say, simple arithmetic operations. You be the judge of how simple that is. But so when we're doing simulations, if we set the seed to the same thing every time, then my results are repeatable. That means other researchers can reproduce my results and verify that I did what I said I could do. So we do this in research to make sure that we have accountability. But it is good to know that if you set the seed for any of these random number generators, you'll get the same exact random sequence every time. Okay, so that's it for the continuous uniform distribution. We've done the moment generating function, the mean, the variance. We've seen how those are calculated. We've talked about the application of it. So don't forget to scan in your lecture notes and upload them before midnight of the date listed on the course calendar. You will definitely want to update your list of distributions. Maybe you want to update the remarks, but you might want to actually put that remark on your distribution list with the uniform, but that's up to you. If you have questions, come to virtual office hours. If you can't, email me, send me a picture of the problem, send me a picture of your work. If you send both, I'll be able to help you by email faster. I hope you'll take care of yourself, and we will see you next time.